Today, we're going to finish up this little section on the convergence and the energy norm. But before I do that, I wanted to go back and address a couple of points where I thought I had made a mistake in one case, and in fact I had. So we went back and corrected that. And in another case, uh, where I thought we had a mistake, it wasn't actually a mistake. So let me go back for a moment to Richardson's method. And the proof that we had for Richardson's method was fine. It was just that I had the wrong, um, I had a omega inverse where I should have had omega. And when I described the splitting to begin with, it should have been omega inverse. So in the notes and in the slides, which are now posted on Canvas, and by the way, if you're following along on YouTube, then these notes or sorry, these slides, lecture slides can be found on a GitHub directory, and that is linked in the show notes of that uh, of every video. So in the lecture slides, this is now corrected, and so that was wrong. But actually, the proof that we had turned out to be correct because I had reverted back to the alternate definition. I had reverted to this one without kind of realizing it. The second error that I thought I had made was in the identification of the general or the iterator matrix for the multiplicative uh, scheme. And so we were talking about this guy, and it turns out that's completely correct. Or at least it corresponds to what we give later. It's in harmony with what we give later for the iterator matrix for this symmetrized multiplicative general linear iterative scheme. Very hard to say. So there was no error for that. Just wanted to bring those two to your attention. So there was an error with the Richardson's method, no error with respect to this symmetric multiplicative general linear iterative scheme. So last time we were talking about the convergence in the energy norm. We got through one of the results and we're partially and now we want to talk about a couple of other things as well. So the result that we did prove was this one. If you have the coefficient matrix being SPD and the iterator matrix is symmetric and invertible, and we defining this matrix Q, which is B inverse minus 1/2 A, we find that Q is SPD, then the general linear iterative scheme given by this iterator matrix B is unconditionally convergent with respect to the A norm. So that's what we proved last time. I won't go through that again. So now we want to generalize that result a little bit. And here's how we're going to generalize that result. So in the last theorem, we assumed that that Q matrix was symmetric positive definite. But I want to look at the case where that Q matrix may be positive definite in some sense, but not necessarily symmetric. So this will give us a slight generalization of that last fact. So now I want to give you a result which is completely general. I didn't have to use the matrix Q here, but it's evocative of that definition that we used previously. So it doesn't have to be Q in this case. It could be A or B. What I want to say is, well, suppose that this Q matrix, just some n by n matrix, is positive definite in the following sense. So with respect to the Euclidean inner product, what this means is that we have Y transpose Q Y. That's what we get by using this Euclidean inner product. If we find that this number is always positive for every Y which is not equal to the 0 vector, however, Q is not necessarily symmetric. Okay, if that happens, then this is not going to be an inner product because Q is not symmetric. However, this object here is going to define a norm. This object here will define a norm. So how does it do that? So that's what we want to prove. So let's suppose that Q is not symmetric, because if it is symmetric and we have this positivity property, then Q is positive definite, symmetric positive definite. And so we already know that that's going to define a norm. So let's suppose that Q is not, symmetric, but still has this positivity property. We want to see that this still comes out to be a norm. How is this possible? So what we're going to do is we're going to write Q as its symmetric and antisymmetric parts. You can always do this for any matrix. So the symmetric part, or to obtain the symmetric part, you take the average of Q and Q transpose. So 1/2 Q plus Q transpose is what we call the symmetric part. The antisymmetric part is 1/2 Q minus Q transpose. Now the symmetric part turns out to be symmetric. You just take the transpose of that and you'll see it quite quickly. This one is symmetric, but what about this guy? This guy is what we call antisymmetric. If I take the transpose of that, I get minus the original matrix back. So not the original matrix, but minus that. Now, by the way, if Q to begin with is symmetric, then this is just 0. All right, it has no antisymmetric part. However, in general, it follows that QAY, Y in the Euclidean inner product is always going to be 0. And that's easy to show. Let's suppose that you have some arbitrary Y. Let's examine what this guy looks like. QAYY. Well, that's by definition just Y transpose QAY. All right, so if I take this object here, let's think about what that is. That's simply a number. Okay, it's a 1-by-1 matrix. So is a 1-by-1 matrix symmetric? Yeah, it is. It's always going to be symmetric. So I can take the transpose of a 1-by-1 and it gives the exact same thing back. So let's take the transpose of this 1-by-1 matrix and let's use a property of transposes. The property of transposes that we're going to use, that you should recall, is that if I have the transpose of any product, then that's the product of the transposes, but in reverse order. So that's the little fact that we're going to use down here. So take the transpose. Again, this is just 1-by-1, so it flips all the orders. But now what do I know about this middle guy? Once I take the transpose of it, because it is antisymmetric, sometimes called skew symmetric, we get a minus sign. Okay, it's the original matrix, but with a minus. And so I can just rewrite all of this as minus the inner product, or something which looks like the inner product, QAY, Y. I guess that is the inner product. So what do I know about such numbers? So I have a number which is equal to its negative. So remember, this is a number, this is a number, this is a number. A number that's equal to its negative. Well, there's only one number that has that property, and that's 0. So this has to be equal to 0 to begin with. And that's exactly what we wanted to show. Now let's consider what we had before. By assumption, we have that QYY is greater than 0. That's our assumption. All right, but now let's replace Q with its sum into its symmetric and antisymmetric parts. So, and then we're going to use the distributive property. We're going to use the linearity of inner products. That's going to give us two separate terms, QSYY and QAYY. But we just showed that this guy is equal to 0. All right, so that says that QS actually must be positive definite. In fact, it's symmetric positive definite because QS is a symmetric matrix. So this is ultimately equal to this. The positivity of this for any Y means that QS is not just symmetric, it's symmetric by construction, but also positive definite. So QS is symmetric positive definite. Since QS is symmetric positive definite, then of course this is a matrix. We know that to be true. Sorry, this is a matrix norm. No, I said, let me back up. I made a bunch of incorrect statements all in a row. This is a vector norm. Okay, since QS is symmetric positive definite, this becomes a vector norm. So why is ultimately this a vector norm then? Well, that's because if we look at that guy, I don't have any room to write it there, so let's do it here. We just showed that that's equal to QS W plus, and this is QA WW, and that's equal to, this guy goes away. So that's QSWW, and of course that's equal to WQS. So this is actually pretty simple because it turns out this is just equal to the to this vector norm, and this vector norm is given to us by this symmetric positive definite matrix. So it's ultimately saying if I have a Q that has this property, even though it's not necessarily symmetric, I can generate a norm because this is equal to its symmetric part. Okay, this is equal to the norm generated by the symmetric part of Q. Okay, so this allows us to prove another interesting result. So let's suppose that A is SPD and B is invertible. And this time, let's suppose this is not necessarily symmetric, but it is positive definite in the sense that we just mentioned. Okay, not necessarily symmetric, but positive definite in the sense that we mentioned. Then the general linear iterative scheme with respect to is convergent with respect to the A norm. And of course, we mean the general linear iterative scheme defined by B, in case you need to be reminded of that. The general linear iterative scheme defined by B is convergent with respect to the A norm. That is, we get this type of convergence. In fact, we can prove that it's monotonic convergent. And the proof goes exactly the same as we did as the proof before. In the proof before, we noted at some point that this was a norm. Well, that was because Q was symmetric positive definite. Now we only know that Q is positive definite by assumption. All the other assumptions are the same. However, this is still a norm, so all of the results that we just proved still hold, or all the calculations that we just used hold true still. So there's really nothing to prove. Once we've established that this object gives rise to a norm, a vector norm, even though it's not symmetric positive definite, only positive definite, then the calculation that we did before holds, and the method is unconditionally convergent. Okay, so we're going to use that one a little bit later when we analyze the Gauss-Seidel method. Let's also prove a more famous result called the Householder-John theorem. It's, again, in the same vein. What did the previous two theorems do for us? Well, we had this, the first big assumption was that A was symmetric positive definite, and then we had this iterator matrix B, which defined some general linear iterative scheme. And then we constructed this thing called the Q matrix. Okay, Q matrix previously was equal to B inverse minus 1/2 A. And if we found out that that was symmetric positive definite or only positive definite, we could show that in the energy norm we had convergence. So now we want to prove a similar result, but using a different Q matrix. So the Q matrix in this case is going to be this one. Q equals B inverse transpose minus A. And by the way, just in case I failed to mention it, what is the definition of B inverse transpose? Well, it's just either the inverse of the transpose of the inverse, or, as I just said, it is the inverse of the transpose. So they're the same object. And so that's why we write B minus transpose. It just saves us a little bit of extra writing. So it's either the transpose of the inverse or the inverse of the transpose. Because those are the same thing, we can just use this simplified notation. So we're starting with this assumption. A is only non-singular and symmetric, and B is invertible. And now we're going to assume that this matrix is SPD. Okay, this odd-looking matrix is SPD. Then the general linear iterative scheme with the error transfer matrix equal to T, error transfer matrix T equals I minus BA, as it's always defined, converges unconditionally if and only if A is SPD. If A is SPD, then the convergence is always monotonic, and we see that the energy is monotonic, or sorry, that the error is monotonic in the energy norm. That is, it's always decreasing. Okay, so one of these directions turns out to be not too difficult to prove, and the other one is quite a bit more difficult. I give this problem in my class on numerical analysis, so many of you have seen it before, and you know how difficult is the other direction. And there's a solution out there floating around that I've given to my class previously for the other direction, but I'm going to leave it as an exercise here. And I'm only going to do one direction. So the one direction that I'm going to show is this one. I'm going to assume that A is SPD and show that the method converges unconditionally under that assumption. This is the so-called easy direction. The other one is the more complicated one. So let's do just that. Let's suppose that A is SPD. We know then that if A is SPD, then this object is a vector norm. The error equation is always equal to that. Remember, that's almost the definition of the error equation. It is the definition of the error transfer matrix. That's where we got or found out that that thing was important. So this is just another way of writing TEK. So let's start with this as our starting point, and let's do some manipulations with that, and try to do some manipulations so that we cook up or find somewhere along the way this matrix appears. So how do we do that? So what I'm going to do is I'm going to calculate the A norm of EK plus 1, and I'm going to square that. Well, EK plus 1 norm squared, that is just going to be this whole object, A norm squared. So what is the A norm of this guy squared? What does that look like? Well, that's just exactly equal to this object right here. Okay, that is everything that you see here. That's the A norm squared. And maybe the way you can see that is, remember what the A norm is. If I have a generic W in the A norm and I square that, well, that's just equal to W transpose A W. And that's what I have here. So that's the first object. That's the transpose vector, and then times the matrix A in the middle and times the vector at the end. Okay, so I hope you see what's going on there. Now, let's distribute this transpose over this product. So remember, that becomes the product of transposes, but in reverse order. So I take the transpose of EK and I multiply that times this matrix. Again, we have A here and the same product we had previously. All right, and let's distribute this. over that product. So we get that. And distribute the A through this product, and we have that. Okay, so A times the identity times EK, that's just AEK. And then this part here gives minus A times B times A times EK. All right, let's keep foiling this thing out and see what we get. So as we do that, for this term times that term, we get that. Then we have these terms, this product, that's just that. And now we do this term times that. That's the outside in the FOIL process. So that gives me that. And finally, the last term in the FOIL product gives me that. Okay, so there's the full FOIL. Now let's collect some terms. So the first term is kind of easy. That's just going to be the A norm of EK. And it follows this pattern here, right? That's the A norm of EK, but with the square. That's good because I'm ultimately, my mission here is to show that when I take the A norm of this EK plus 1 squared, I'm going to turn up A norm of EK squared on the right-hand side plus some junk, which I hope to be, I can write as maybe some norm. Well, I do a couple of steps here in a row. The first one is to pull out a couple of common factors, use distributed property twice. So I'm going to take any product which looks like this, EK transpose A, and I'm going to pull it out of the front. That appears in every one of these terms here. Good. So there's 3 terms there, pull it out. And on the back end, I'm going to pull out A times EK. And there are 3 of those terms. And what I'm left with is something in the middle, which looks a bit familiar. This looks like the iterator matrix for the symmetrized multiplicative schemes that we defined earlier. I can pull out on this side, I can pull out a B transpose, and on this side, I can pull out a B. And if you do that, now we're going to use the assumption that B is invertible. And what's left in the middle is B inverse plus B minus transpose minus A. Now, the way you can see that this is equal to each other is basically we're just trying to show that this is equal to this using 2 distributive properties, one from the left and one from the right. To see that it's true, just multiply this back through. Okay, so we've done this before, and I hope that you can see that those 2 objects are equal to each other. Well, now this is the Q matrix that we just defined. In fact, at this point, I could have just replaced this with Q. And we also notice that this is the transpose of a certain product, namely BAEK. And so I can use that property of transposes. And notice that this product on the right is exactly the same, but it's missing the transpose. So this whole thing is it's really a norm squared, where this is the norm, or sorry, the matrix sandwiched in the middle, which defines the norm. And then this is the vector that appears on both sides, one with a transpose and one without. And it's kind of in this form. I hope that you can see that. But this matrix is what we called Q. So I'm going to do 2 things in obtaining this simplification. I rewrite this, or recognize that this part here, this matrix is Q. So that whole thing is just equal to minus the Q norm of BAEK, and it's squared. And then what I do is I'm going to move it to the other side because it comes with a minus sign. And that's where this term comes from. A norm of EK plus 1 squared plus a Q norm of BAEK squared, and then equals to the A norm of EK squared. So you can see that to obtain the K plus first step, I have to add something on to it in order to get to the kth step. Or let me say it like that, or let me say it in another way. This must be smaller than this because I have to add something positive or non-negative to it. So that says that that sequence of the A norms of EK is a decreasing sequence because I have to add something to this norm, namely that, in order to get the previous one. And this something is something which is non-negative. So that proves that this sequence is decreasing. Now I'm going to invoke the monotone convergence theorem. So the monotone convergence theorem automatically implies, because I have a decreasing sequence that's bounded below. By the way, what is it bounded below by? By what number? Well, it's got to be 0 because all norms are non-negative. So it's bounded below by 0. It's monotonically decreasing, so it has to converge to some limit. So let's call that limit alpha. All that we know about it is that it has to be greater than or equal to 0. But we know that both EK and EK plus 1 in those norms have to converge to the same limit. So that's just a property of sequences. If I change the index by 1, it's not going to change anything, really. It's not going to change the limit. So if both of these guys have the same limit, and let's just look at this equation that I have here. This holds true for any k. If this converges to alpha and this converges to alpha, then this must converge to 0 in the limit. Or in other words, if I want, I could move this guy to the other side, and you can see that the difference converges to 0, and so this has to converge to 0. But as it is, this has to have some limit because this is going to have limit alpha, and this is going to have a limit alpha. So that just says that this guy has to converge to 0. All right, but what does that mean? Well, that means that this whole vector has to converge to 0, but this is an invertible vector on the front, or sorry, an invertible matrix. All right, so it's a property that you've seen in linear algebra. If I know that if I have an invertible matrix, let's call it the C matrix times some x, okay, and that's equal to 0. Well, I know that the only way that this can be possible is if x is equal to 0. So that's the limit point. And that's because C is an invertible matrix, right? The only vector an invertible matrix maps to the 0 vector is the 0 vector itself, or in other words, the kernel has to be equal to just 0. All right, so that's basically, that says that the limit of EK has to be 0, and that's exactly what we wanted to show. That's unconditional convergence. So that means if we assume that, let's go back to our assumptions. If we assume that this is SPD and A is SPD, then the general linear iterative scheme converges unconditionally. The other direction is much harder, or it's at least a bit harder. If I assume that this converges unconditionally, and this is symmetric positive definite, then we can show that it must have been that A is symmetric positive definite to begin with. That direction is left as an exercise, but as I said, it's a bit harder. Well, now that gives us this famous, or at least this theorem whose name is well known, the Householder-John theorem. So let's apply these last few theorems to prove that the Gauss-Seidel method converges. Well, to do this, we have to start by assuming that A is SPD. The coefficient matrix in the problem that we want to solve is SPD. So remember, what we're ultimately trying to solve is this problem, AU equals F. The coefficient matrix is assumed to be SPD. Then let's prove that the forward, backward, and symmetric Gauss-Seidel methods are all well-defined and they all converge. Well, they're all well-defined because, essentially because the diagonal matrix has to have positive elements in it. That's a fact that follows from the fact that A is an SPD matrix. So the diagonal elements all have positive elements. That means that the Gauss-Seidel method either the forward, the backward, or the symmetric is going to be well defined. You can actually compute with it. Well, now let's use one of our theorems to prove the convergence for the Gauss-Seidel method. And in particular, let's use the Householder-John theorem. In the Householder-John theorem, it says, well, you have to take the B matrix inverse, okay, plus the B matrix minus transpose, and subtract off from those the A matrix. If we can show that that resulting matrix is symmetric positive definite, then that will guarantee that our method converges using this Householder-John theorem. Well, now here's how it goes. So we know what the iterator matrix is for the Gauss-Seidel method. It's the inverse of D minus L. Okay, so if I take the inverse of inverse of D minus L, I get precisely D minus L back. All right, and now take the inverse transpose of inverse D minus L, you get D minus U. Okay, so that's remember, we're using here that we're using the fact that B is equal to D minus L. So B inverse is just equal to that, and B inverse transpose is D minus U. Short little exercise shows you that. A is equal to D minus L minus U. So if I have minus A, I get minus D plus L plus U. And then we get a lot of cancellation. Minus L minus U cancels with plus L and plus U. And I get two D's minus a D. That just gives D. So the question is this matrix symmetric positive definite? Well, it's a diagonal matrix with positive diagonal entries. And so it's almost trivially symmetric positive definite. So that means that we can use the Householder-John theorem to prove that the Gauss-Seidel method converges unconditionally, right? So that's Householder-John applied to the Gauss-Seidel method. And you can see that the proof took us just a couple of lines. Now, think back to the to the previous theorem that we had about Gauss-Seidel, the convergence of it. We assumed that the stiffness matrix was strictly diagonally dominant, and that proof was a lot longer. Yeah, so one of our students points out a very interesting fact. I like to echo that as well. Householder was a professor here back in maybe the 60s, 70s. I think it was 60s and 70s. But yeah, this Householder guy, and he's well known for this procedure or these objects called the householder reflectors and the householder reflector method for orthogonalizing a matrix. So yeah, he was here at UT. And he also had a joint appointment at Oak Ridge. So yeah, thanks for pointing that out. So this gives us a nice, short, fast, fun proof that the Gauss-Seidel method converges unconditionally as long as we are assuming that A is SPD. We could also use a corollary to one of our previous results. And let's do that. So the corollary said that if we had this Q matrix defined as B inverse minus a half A, if we could find that that was positive definite, didn't have to be symmetric, just had to be positive definite, then we could use that corollary to show convergence as well. So let's do that. So remember, keep in mind that B for Gauss-Seidel is just going to be D minus L inverse. Okay, so as our starting point, we take the inverse of this guy. So that's just D minus L. And then we subtract from that 1/2 A. So 1/2 A is going to be minus a half D plus a half L plus a half U. And so what we get from that is this mess here. All right, so now we need to show that that guy is positive definite. But it turns out there's a kind of easier way to do this. And the easier way is let's just show that the symmetric part of this Q2 matrix is symmetric and positive definite. And if we can do that, then that takes care of it. That takes care ultimately of everything we want to show. So let's calculate the symmetric part of this Q2 matrix. So Q2 is this, which we ultimately showed was that. Here's the symmetric part of it. Take the symmetric part of this, do the calculations, you find you get 1/2 D. So the question is this symmetric positive definite? The symmetric part, this Q2 matrix, well, it's equal to 1/2 D, and D is a symmetric positive definite matrix, so check. So that corollary that we had to a previous theorem a couple of slides ago gives us that the Gauss-Seidel method is convergent. Okay, so another way of doing it. By the same techniques, we can show that the backward Gauss-Seidel method is convergent. In the backward Gauss-Seidel, you just use the fact that the iterator matrix was equal to this matrix, D minus U inverse. And you can repeat the same two calculations that we did, one using the Householder-John and one using that corollary. Now let's finish up. So the last thing we might want to do is show that the symmetric Gauss-Seidel method is convergent. And for this one, let's use the Householder-John theorem. So for the symmetrized Gauss-Seidel method, or the symmetric Gauss-Seidel method, so you may recall that that iterator matrix is given by that product. Okay, so it's all these matrices here. So D minus U inverse times D minus L inverse. Well, as a short exercise, you can show that since this is our iterator matrix, if I take the inverse of that, remember, I'm going to use the property of inverses, which says that if I have a product of two matrices, each of which is invertible, if I take the inverse, then it's the product of inverses, but in reverse order. So I'm going to use that property. Take the inverse of this, take the inverse transpose of that, okay, and then subtract from that sum, subtract A. And what you get is, I contend, A plus 2U transpose D inverse U. So the question is this symmetric positive definite? Well, it is. It's maybe not completely obvious, but here's the reason why. If I have two symmetric positive definite matrices and I add them together, then I get another symmetric positive definite matrix. That's a known property. Well, A is symmetric positive definite, but what about this guy? This one is also symmetric positive definite. So D inverse is symmetric positive definite. If I pre-multiply by U transpose and post-multiply by U, this product is still symmetric positive definite. Actually, this matrix may not be symmetric positive definite. It may be what we call symmetric positive semi-definite. Okay, so you might remember the distinction between symmetric positive definite and symmetric positive definite from numerical analysis. So there's this concept called symmetric positive definite, and then there's symmetric positive semi-definite. All we need is that this guy is symmetric positive semi-definite. In any case, we're guaranteed that that's true. And since this is symmetric positive definite, the whole thing, which we call the Q matrix, is symmetric positive definite. So we can apply Householder-John theorem. And since that is symmetric positive definite, then the symmetric Gauss-Seidel method converges unconditionally. Okay, so that is end of chapter 1. Okay, so now we're going to get into chapter 2 of our lecture notes on multigrid methods. And so in lecture 2, we start to describe actual non-classical stuff. So up till now, everything has been the classical iterative methods that you would have seen in your introductory numerical analysis sequence. Now we're going to start talking about things which start to look like multigrid methods. And we're going to start with a kind of half multigrid, and that's called the two-grid method or the two-grid algorithm. So this is chapter 2, two-grid algorithm. And it looks like actually we only have, chapter 2 is kind of short. but chapter 2 is really just about introducing notation, definitions, and concepts. And so there are only 3 sections, kind of short, but I really just want you to know what are the key components of this 2-grid algorithm. So we're going to give the basics of 2-grid, and the idea is why are we doing this? Because multigrid is essentially a recursive form of the 2-grid algorithm, and that's how the two are related. So the approach we're going to use is going to continue in the line of the things we were doing previously. We're going to use matrices rather than operators. This helps us to understand how the dimension's constantly changing in going from what's called a fine grid to a coarse grid. We won't connect to PDEs yet. That's coming soon. We're going to keep everything to be completely generic so that we can apply this in any sort of situation. So in chapter 1, we didn't introduce any kind of differential equations, no PDEs. And in chapter 2, we're going to keep with that. And then finally in chapter 3, we'll see what PDE are we going to solve? How do we motivate what we're doing? Okay, so we're going to show that this new object called the 2-grid algorithm is actually just kind of a fancy general linear iterative scheme. It's going to be a lot more complicated, a lot fancier, but it's going to have the same basic generic structure that we've already seen. So we know how to analyze that. We have to calculate the error transfer matrix, et cetera, and so that's kind of how we're going to do this. We're not going to anymore use the kind of old-fashioned spectral theory that we developed in chapter 1. We're going to use the second, more modern approach, and that is the one that uses the energy approach. So we'll introduce certain energy norms, and that's going to be how we do it. So let's talk about the components of the 2-grid algorithm. What are the key components that go into this soup? So the first thing we need is 2 SPD matrices. And to construct these, well, I'm not going to really construct them. I'm just going to assume that they exist and they have certain properties. Let's start off by assuming we have 2 natural numbers, n1, which is bigger than n0. So n1 and n0, where n1 is bigger than or equal to n0. They could be the same, but usually this one is like twice as big as n0. That's the idea. And let's suppose that we have lying around a matrix A1, which has dimensions n1 by n1. In other words, it has n1 rows and n1 columns. So that's the bigger dimension. Suppose that that guy is SPD. We're going to call, kind of arbitrarily so, we're going to call this A1 the fine grid stiffness matrix. All right, the fine grid stiffness matrix. Why is it called the fine grid? Well, this is going to be explained as we go along. Why are we even referring to something as grid? There's no grid yet. And that's true. There's no grid yet. And you don't have to think about a grid. We're operating in very generic terminology, very generic framework. Now suppose I have another matrix called R, which is not square. It has a few rows and a lot of columns. So this R matrix, so first of all, we have A, which kind of is like that. And R is, let's see, it looks a bit like that. Right, so we have N1 rows, N1 columns, and this one has N0 rows and N1 columns. Okay, so I can multiply those 2 matrices together. So this would be R0 and this would be A1. All right, now I want that matrix R0 to have full rank. Okay, so what does that mean? That means its rank is equal to the lesser of those 2 numbers, which is N0. So full rank for R0 means it has rank exactly equal to N0. Now, that R matrix is what we call a restriction matrix, and we'll explain why it's called a restriction matrix in a few chapters. For now, this is just a definition. We could call it a cat or a dog or an elephant. It doesn't matter. Mathematicians You're free to do whatever you want. You can make any definition you want as long as it's useful. We're going to define something called the prolongation matrix. And the prolongation matrix is just the transpose of the restriction matrix. It's always related in this fashion, at least in this course it's going to be. It doesn't have to be for multigrid to work. But this is what we're going to do in this course. Later on in chapter 7, we're going to talk about cell-centered finite difference approach and multigrid. In that case, we may break this structure there just for just so I can show you that you can do it and things still work. Now we're going to define, or we're going to introduce another matrix which is of smaller size called the coarse grid stiffness matrix. Coarse grid stiffness matrix. It's also going to be an SPD matrix. So this guy's SPD A1. Coarse grid matrix is also going to be SPD, and it has dimension of the smaller of the two, N0 by N0. Now, I didn't complete my picture here. Completed picture would be, so ultimately I'm going to multiply R times A times P, and this guy has P has N1 rows and N0 columns. And then I'm going to ask a question. I have this smaller stiffness matrix, N0 by N0, which we call A0. And the question is this matrix equal to this product? R times A1 times P, so R0, A1, P0. Is A0 equal to that product? If it does equal that, we say that the Galerkin condition is satisfied. Okay, so if A0 is the symmetric positive definite matrix equal to this product, then I say that A0 satisfies the Galerkin condition. Now, here's the first question. Does this even make sense? Well, let's look at the multiplication. Am I allowed to multiply R times A times P? Answer, yes. They are compatible for multiplication because the number of columns here equals the number of rows here, and the number of columns here equals the number of rows here. And we can even figure out what is the size of this product. The size of this product is going to be N0 by N0. The next question I would ask is, well, that has the right size, but is it symmetric? Well, if I take this product and take the transpose of it, I take the product of transposes in reverse order, you'll see that because I assume that this is symmetric and the way that these are defined, then I'm going to get the same product as when I take the transpose. So the whole thing is symmetric. The last question I want to ask is this product symmetric positive definite? So we saw that it's symmetric, okay? And now the question is it positive definite? And the answer is yes. And that has to do with the fact that R0 and P0 are full rank. If they weren't full rank, then it wouldn't be symmetric, or then it wouldn't be positive definite anymore. So this product is always going to be guaranteed to be symmetric positive definite by my construction. And this guy is a symmetric positive definite matrix. If this one equals this product, then we just say that these are related through what's called the Galerkin condition. The Galerkin condition. So for now, that's just a definition for you to put in your back pocket. Ultimately, what I want to do is I want to solve this problem. This is a symmetric positive definite problem. And I'm going to assume that this vector is just some given vector in Rn1. So I want to solve this problem. How do I do it? Well, we've already been introduced to a number of ways to solve this using approximation techniques. We have Jacobi, weighted Jacobi, damped Jacobi. We have Gauss-Seidel, symmetric Gauss-Seidel, backward Gauss-Seidel. We have Richardson's method, etc. So those are iterative methods that can be brought to bear on a problem like this. But you have to keep in mind, this is the problem we want to solve. So where does this coarse grid stiffness matrix come into play? Well, that's what I need to show you and motivate for you. So here's exactly the picture I drew before. Everything is compatible for multiplication, R naught times A1 times P naught. And I get an N0 by N0 matrix. And because R naught and P naught are assumed to be full rank and A1 is symmetric positive definite, then this product will be positive definite. And if the Galerkin condition holds, all we're saying is that A0 matrix pops up or is the result of this product. All right, so if A1 is SPD and A0 satisfies the Galerkin condition, then A0 is also SPD. So that one we already said. How do you show it? Well, you just take the transpose of A naught, since it's given as the Galerkin condition. By the way, the Galerkin condition is what I also call the RAP condition, RAP RAP. So I'll constantly be calling that the RAP condition or the Galerkin condition. If I feel lazy, I say RAP. So take the transpose of A0 given through the Galerkin condition, and you find you get A0 back. And this just has to do with the symmetry and the construction. What about the positive definiteness? Well, suppose that W is any vector in Rn naught. So this is the smaller vector space. Suppose that it's arbitrary, but it's not equal to 0. Since R0 is full rank, then it turns out that this product can in no ways be equal to the 0 vector. Okay, since this guy is full rank, okay, R0 transpose times W cannot be equal to the 0 vector. Okay, that's just a fact that follows from the assumption that R naught has full rank. So let's follow through with this product. W transpose A naught times W and replace A0 with the Galerkin condition. And we're going to group this product together, R0 transpose times W. We'll notice that this is just R naught W product transposed, which is what I have here. I might have said that incorrectly. R0 transpose W, all of that product transpose. So that's what I have on the left-hand side, and what I have on the right-hand side is the same. But remember, my assumption is that A1 is not equal, or is A1 is symmetric positive definite, and there's no way that this matrix or this product here, this vector, can be equal to the 0 vector. Well, since this is symmetric positive definite, then this product has to be positive. And so that's where the positivity comes from. So symmetry, positive definiteness, that gives us the SPD-ness. So if A0 is introduced as through the Galerkin condition, then it's guaranteed to be SPD. We don't have to assume it. Now, what does the actions of R naught and P naught look like? Well, remember, R naught has N0 rows and N1 columns. So that means if I take a vector that is in N1, that means it's a large vector, then what happens to it? So it may be easier to just see this by a drawing. I have N0, N1, and I have a big vector that I'm multiplying it by. So it has N1 entries. Well, this turns it into a small vector having only N naught entries. So what the restriction matrix does is it takes a lot of information and it squishes it into a little bit of information. So in information theory, we call this a lossy process, or in other words, this is a process which destroys some information. You know, unless this is mostly populated by zeros, actually even zeros is information. But if you have a vector storing n1 bits of information and you replace that with a vector containing n0 bits of information, you have lost information. There's no way around it. So the the action of the R matrix destroys information. It takes something from a high dimensional space and puts it into a low dimensional space. Conversely, the P matrix takes information from a low dimensional space and puts it into a high dimensional space. The picture is like this. So the P matrix is tall and thin. So it has n1 rows and 0 columns. And I multiply that times a vector which has a small amount of information, n0 bits of information, say. Okay, and so it transforms that into a tall vector having n1 pieces of information in it. So what am I doing in going from this to this? I'm creating information. Or another way, so one way you can think about it is you're using some sort of interpolation method to fill in the blanks. So this is the R matrix and this is the P matrix here. So R destroys information by taking big vectors and putting them into small vectors. But the P matrix does the opposite. It takes a small vector and increases it. So it's creating information somehow. Okay, so it moves something from a low dimensional space into a high dimensional space. Now, you've probably seen in the past, these types of matrices were called projection matrices. They push something from a high dimensional space to a low dimensional space. So these types of matrices are similar, these restriction operators. So you push something from a high dimensional space to a low dimensional space, that's going to be restriction. Multigrid has its own set of terms you'll see in terminology. And so that's why the difference in notation and terminology appears, because multigrid culture is just a little bit different than everything else. So keep that in mind. Restriction destroys information. Prolongation is the opposite. It creates information. It takes something from a low dimensional space to a high dimensional space. And if you're ever wondering which one is which, just draw these pictures out and you'll see. Now, where does the grid aspect come in? Well, usually in multigrid, we're applying these operations to data which lives on a grid. So suppose I have this grid of data here. So this could be thought of like a vector, and each one of these filled dots contains some information. Like, for example, this might be -2, and this one would be 3, 7, 8, -6, 5, and 1. Okay, so there's information that lives there. We're going to take our restriction operator and push this information from a high dimensional space into a lower dimensional space. So in this case, we might take the average of these three numbers and put it into that. However, however we're doing it, we're taking a bunch of information from a high dimensional space and we're pushing that into a low dimensional space. So this is kind of what restriction does. Restriction takes from a high dimensional space to a low dimensional space. Where did these level ideas come from? Well, we're going to call the space with more information in it, we're going to call that level 1. So high information or lots of information, that's a level 1 piece of information, and a level 0 has less information. Okay, so this we can think of as the fine grid, and this we can think about as the coarse grid. So that's where this terminology is coming from. Prolongation has the opposite effect. So you're starting with something which has a few pieces of information, and you're kind of broadcasting that or creating more information from that. So prolongation takes you from a coarse grid. This grid, let's say, has only 4 points, 1, 2, 3, 4, and it's going to push that information into a grid which has 8 pieces of information in it. So it's going to effectively double the amount of information. So this one's going to create information. Now, as I said before, we're going to be given a vector in our high dimensional space, and we already have this A1 matrix from our high dimensional space, which is symmetric positive definite. And we're looking for a true solution to this problem. And just to make things really concrete, I'm going to give that an extra symbol E for exact solution. So the exact solution is going to solve this problem. To find an approximation to the exact solution, we're going to create a sequence of approximations through what is called a two-grid operator. So I have to define this two-grid operator, but basically it says if I put in the F1 information and the U1 information at the level K, I'm going to make it better, create a more, usually a more accurate approximation at level K plus 1. So this is our iterative process, and this operator we call the two-grid operator. Again, I'm giving things in a very in general terms, and we're going to come back and motivate this through examples later. So my first order of business is to define this thing called the two-grid operator. And I have to define this in 3 stages. So how does this go? So let's suppose that you're given some data G1, and this is a bit like the true solution data here. And the reason I'm not calling it F1 is because I can really put anything in there. I can put anything into that slot. So I'm going to give it a generic name G1. So you give me G1, that's kind of like my F1 data. And I'm going to give you an initial guess at the solution. And I'm going to try to invoke some approximation scheme, some linear iterative scheme to make that approximation better. And I'm going to do it through 3 stages. So the 3 stages go, actually 4 stages, because there's the initial, and then I'm going to improve that in 3 different stages. Now, the 3 stages that I'm going to improve this are smoothing, or what's called pre-smoothing, what's called coarse grid correction, and then finally what's called post-smoothing. So I have to define these 3 steps. Okay, so the first one, pre-smoothing, all this is I'm just going to take this initial bit of information here and I'm going to copy it over. Okay, this copy step doesn't need to happen, but it's just to emphasize I'm copying this information and now I'm going to affect some change on it. I'm going to call that copy 1, 0, superscript 1, 0. And here's how I'm going to improve this guy. I'm going to run it through this process. Now, what does this process look like to you guys? Does it, you can nod your head. You don't have to tell me. Or if you want to get on, use your voice, you can say what it is or say in the chat. What does that process look like? A general linear iterative scheme, exactly right. So this process here is just a general linear iterative scheme. What is the iterator matrix for this? What's the iterator matrix for this one? Yep, just S1. It's just whatever this guy is here. So this looks like I'm solving a certain problem with a general linear iterative scheme using an iterator S1, and I'm indexing by this parameter sigma. So I get sigma plus 1 from sigma by a general linear iterative scheme, and I'm going to run this sigma process, or this pre-smoothing. I'm going to do this M1 times. Okay, so I'm going to do it M1 times. So this is 0, and then I get 1, and then 2, and then 3, and I stop whenever I get to M1. Okay, so this one is not, let's see, is it multiplicative? The way you should think about it is I'm not thinking about multiplicative. I'm simply doing the same single process, but I'm repeating it M1 times. But now let's see, is it multiplicative? Yeah, I guess it kind of is multiplicative, but it's multiplicative, but you're using the same iterator matrix. Okay, if that makes sense. So it's not multiplicative in the sense of changing iterator matrices, but you're doing this in sequence M1 times. Okay, so just notice that this guy stays the same. So you pick that iterator matrix and you just use it. All right, so after I do M1 steps of applying this GLIS method, then I'm going to call that the pre-smoothing stage, and I'm going to copy that into U11. Okay, pre-smoothing is now finished. Now, why is it called smoothing? Well, this is going to get to the heart of multigrid, and something I'm going to explain in a few sections. Okay, why is it called smoothing? Actually, it's going to be explained in the next chapter. Okay, disregard this stuff up here. Basically, I'm just going on with step 2 now. Okay, so step 2, the next thing we want to do is, now that we have this stage 1 approximation, we're going to improve the stage 1 approximation too. So what we're going to do for the stage 1 approximation is we're going to say, I'm going to compute a residual involving that stage 1. So effectively, you can think, I'm really trying to solve this problem. Okay, UE1 equals G1. And I called it G1 just because I can. But now suppose I have an approximation of that problem. And what's that? What's the residual of that? Well, whatever the approximation is, I can compute the residual of it by taking G and subtracting from that A1 times U1 box. Okay, whatever that box is. Well, in this case, the box is just going to be this thing here, which is the update that I just got after exiting the pre-smoothing stage. So after I apply M1 steps of this GLIS, I get this guy, and that's the exit of the pre-smoothing stage. Now I'm going to calculate its residual. See, that's exactly what I've done. I'm going to call that residual R11. Now I'm going to move this residual from the fine grid down to the coarse grid. So 0 means coarse grid, 1 means fine grid. And the restriction, remember what that does is it takes information on a fine grid and it pushes it into a coarse grid. It destroys information. So I take this residual, I push it down to the coarse grid, and now I'm going to do something with that guy. First of all, I'm storing it in R01. But now I'm going to take that guy and I'm going to compute this from it. Okay. What the heck is this? Well, this looks like, this is just the stiffness matrix at the coarse grid level. And I'm taking the inverse and applying that onto a vector. So what does that look like? What's going on there? Well, suppose I have, remember the error residual relationship. So now let's look at the error residual relationship on 2 different levels. So suppose I'm on level 1. Okay, so this error residual relationship would satisfy this. Now, remember, if you tell me what the residual is, that's some piece of information, but it's not so useful. However, if you tell me what the error is, that is infinitely more useful than the residual. If you tell me what the error is and I know what my approximation is, I'm immediately going to know what the true solution is. So here's how. If you give me an approximation, let's call it U11, and you tell me what is the associated error with that, do I know the true solution? Well, yes, you know the true solution because this is just the exact minus its approximation. So if you tell me what is the approximation and the error, I can use this difference to compute the true solution. So knowing what the error is the same as knowing what the solution is. All right, so if at this stage I was able to compute the error, let's compute it for this this residual that we just computed up here. So if I know the error, if I can solve this equation, that's tantamount to saying what is the true solution. Okay. I'm sorry I went over a couple of minutes, so we're going to pick up here next time, and I'm going to tell you why it is that we're making this step. So this is kind of the crucial step, and I want to spend a few minutes on saying why that's important and what it's useful for. Then immediately I'll go into an example and show you why that effectively doing this step is telling you a lot of information. So we'll pick up there next time. And for you in the local audience, you can turn your cameras back on now and we can take some questions.